Welcome to the stress strain lecture. Mechanical properties of materials typically are measured using the response to imposed loads. And this stress strain relationship is a method of not only discussing the properties of equipment materials, but it's also used, as you can see from some of the previous lectures, about the anatomical structures of the body. So this is what a typical stress strain graph looks like, and it illustrates how stiff or compliant a material is. We will go over each of the components of the graph in more detail, but from a gross perspective, the slope of the load deformation curve illustrates the stiffness of the material, and you can see that in this area here. So we'll talk about what stress is, we'll go over the strain component, and we'll talk about each of the individual components of this further down the line. One of the great areas that this stress strain curve and impact testing is used in the footwear industry. It's made huge changes and advances with the material properties over the last 4 decades. Materials are selected to give the proper feel. They provide adequate support or lack thereof. They're meant to do great shock absorption or maximize proprioception. Additionally, by doing the material testing, changes in stress strain curve, it has been estimated that shoes need to be changed after a certain quantity of mileage. And you hear that range anywhere from 300 to 500, depending on who you talk to. But if we look at this little footwear diagram here, there's more shoe, there's more cushioning, there's less shoe, less cushioning. And each one of these individual shoes has a different mechanical properties based off, here you have a certain type of shoe, and down here you have another brand of shoe. And each shoe company takes and chooses materials that they believe have the material properties that produce the interaction with the environment and shock absorption that they would like. So there's a wide variety of shoes, and being in the footwear and doing some of this research over the last few years, it's one of the questions you get mostly. Do I want extreme cushioning, or do I want something to focus on performance? And by changing the materials and the structure of the shoe based off this material testing, you can have an effect or a perceived effect on those. So before we get further into the stress-strain relationship and how things are oriented, we first need to define a few variables for you. And these are the 2 variables that make up the load deformation curve, and they are stress and strain. Stress, abbreviated by the term sigma, identifies the y-axis. Now it's calculated as the amount or the magnitude of force or load per given unit area. Right, so it's force or load divided by the area at which it's applied. The units of measurement are pascals or newtons per meter squared. And then you have what's on the x-axis, and this is strain, also known as deformation, or it's the quantity of deformation or change in length of that material as the load is being applied. And that's very important. So this deformation and change and strain that we're measuring is while the load is being applied. Okay, strain is a unitless number because it's a change in length divided by the original length. So it's not just how much change is happening, but it's literally, and as you can see in this equation here, that delta or that triangle is change in length over. So if I had meters on top and meters, they cancel each other out. So that's why it's unitless. So it's a very important component. So there are a number of regions of the stress strain load deformation curve, and we'll talk about first just the 2 major regions that we want to discuss, and that is going to be the elastic region here, this first part, and also the plastic region. These are the 2 major regions, and the elastic region is the portion that represents the elasticity of the material. And when elasticity means the ability to recoil and rebound, right? So when the stress strain relationship is within this region, the material will return back to its original length and form following the removal of that stressor load. So there will not be a permanent deformation. So when the load or stress is applied to the material and causes a permanent deformation, you will now move into that plastic region. So this is a very important concept. So what delineates where you're going to be staying here or here is not the straightness or the curvature of the line. It's more what happens as we remove the material or the load from the material. Because once we get into the plastic region, there will be a permanent deformation or change in length, whether it's increased or decreased in length, and it won't return to the original shape. So elastic region, once again, the material returns to the original length once the stressor or load is removed. In the plastic region, once the load is, or stress is removed, there is a different resting length. So one of the key components is what this E stands for right here in the elastic region. And this E is going to be referred to as the elastic modulus. Now, the elastic modulus is the stiffness of the material, and it's calculated as the slope of the line, and typically in the elastic region. So slope, again, is rise or stress over run, which is strain. So it'll be, okay, and so this is the region we're really focused on here. And we're going to use this by taking the rise over elastic modulus represents this relationship between the unit increase of stress per unit increase in strain. So we'll know as I increase a stressor, I should expect this change in the strain because of the material properties. Material with a greater elastic modulus is said to be more stiff, right? So a steeper slope versus a more gradual slope is more stiff. So if I put this as A and this one as B, A would be considered more stiff than B because per unit increase of stress you have, because as you have, it causes more, needs more stress to make the same change in strain, right? So B is more compliant because it has a greater change in its length or deformation as a result of a smaller increase in stress. So a more stiff material needs more stress to cause a smaller change in its length, okay? So steeper elastic modulus, more stiff. A smaller elastic modulus or a reduced elastic modulus is something that is more compliant or less stiff. Now, the next portion of this graph is at some point in between as you're applying and increasing the stress or the load that is being put on the material, there's a point at which the load causes a transition from the elastic region to the plastic region of that material. This point is called the yield point. So at the yield point, it's the point where the material has entered the plastic region because the stress has become great enough to cause a permanent deformation when the load is then removed. So that point at which you transfer from elastic to plastic is that yield point. And it's important to understand that this yield point can happen at different points for different materials, and that's just one key component of some are lower stress, some are higher stress, some allow greater strain, some less strain. So just understand that after you go beyond the yield point, you are no longer able to return back to the original resting length of the elastic region of the material. If you continue once you enter the plastic region to increase your stress or load that's being applied, then there's a certain point the material will change structure through breakage. So not only now will they have a change in the resting length, but there's actually a breakage or a failure of the material. And the failure is when the material not only has a resting length, but it's also, there's been a fracture or some sort of completely changing of the structure. And so that's called your failure. Now the length of this plastic region from the yield point to the failure is going to be different for each individual material. So both from a strain perspective or along the run. So some will have this length, some will have it much shorter, as well as the rise may be different from material. Some may be able to withstand a greater amount of stress within that material once they're in the plastic region. But understanding that this region that we've drawn here is not going to be the same for every single material. This shape could be much different. And some will be much flatter, some will be really steep and stop drastically, and some may be able to drag out much longer. So understand that that concept of yield point to failure is transitioning into plastic, and failure is when there's a rupture or breakage in the material. Now, once you're in the plastic flow region and you don't achieve failure, but you stay in the plastic region and you remove the stressor, it goes all the way back. It follows the path of B. And so this is the return, and we'll talk about what this concept is. But B is a return back to the original resting length. So if I put here L0, that's the original resting length. This is L1 after the load is removed. So L1 is the new resting length after you applied that stress, and the stress then was removed. Now, the residual strain is the difference between the original resting length and the new resting length. So typically it will be L0 minus L1. Okay, so that's your residual strain. It's that change in length that is left over or is a residual following the removal of the stress. Now it's important to note that the new resting length could either be longer or shorter, depending on whether it's a tension or a compression force, right? So if I'm pulling on a spring, at some point I can pull the spring and the spring will not recoil back to its original length. Same with compression. If I compress, think about a slinky or any kind of spring. So it could be longer than its original resting length. So this could be a positive or negative number depending on where you're at. So the relationship between the elastic and plastic regions are easily understood for elastic materials with a linear relationship during the elastic region. And that's like with the footwear and most of your material properties throughout the world. Now, I will tell you, when we do footwear testing, we do a series of impacts before we actually measure it, because we want to heat up the material a little bit, because materials do behave differently when they're warm versus cold. So we want to make sure that the material is to the proper temperature, because if we impact one and then count 10, 10 is going to be warmer, so the property may be different. Now, the interesting part is the human body is not linear in its behavior, and you probably know that. We're more of a viscoelastic or non-linear relationship between the stress and strain. That means that the tendons, ligaments, bones, and muscles kind of change according to how it's, remember we talked earlier about it responding differently to direction, duration, and loads. And so this is a key component here. The nonlinear relationship between the applied stress and strain may have a linear relationship at smaller regions of that portion. And you can see that with E1, E2, and E3. E2, seems like there's a semi-linear relationship for a certain period within this elastic region. But you'll see this little toe, we call this a toe at the beginning of it, which is where it's just trying to reduce some of the slack and get going and get to its more important point. And then it kind of bends out before it gets to that plastic region. And of course, in the human body, this out here is a fracture or breakage of it. But one of the key components that we wanted to make sure you talk about is that there are multiple elastic moduluses depending on where in the loading system you are. And again, if we broke this down to the different components of the elastic region, you could see where depending on how the structure was aligned in its position and tautness and strength and length, you would have different components, right? So think about this being Achilles tendon when you are in plantar flexion, then you go through normal motion, right? And then maybe this is through dorsiflexion where it's completely extended, right? So these are E1, E2, and E3 would be examples of how the length and tension of that gastroc would elicit different mechanical properties in the loading. So the question then becomes, well, how does the stress-strain relationship relate to mechanical energy? So going back to the concepts of a little bit of the footwear, the question that we have is, how do we calculate the mechanical energy by using this relationship? So what I would like to do first is just quickly define what mechanical work is. And that's just the ability of an object to perform work. And one of the things we're going to talk about is It constitutes the actual sum of that motion, but also a huge component of this is that stored energy in the system. So we're going to use, and I'll show you in a second here, this stored to stress strain relationship to try to calculate how much energy is stored within the material. And then we calculate how much is returned. And that's where we're going to look at this mechanical energy concept of the sum of motions, the stored versus returned, and go from there. So describing stored mechanical energy a little bit more for you. We'll have here we have the stress strain curve. And so this is the ability of material to return the stored energy. And so when we load a material, or when a material is loaded, even the human structure, and we'll talk about a little bit later on in the class about running, the material is said to absorb some energy within it as it gets compressed or as it gets extended. So as you're compressing or applying a tensile force to it, the energy underneath this curve, and so that black line right there is the stress-strain relationship, that's the curve. This blue shaded region is going to be the stored mechanical energy, and it's calculated as 1/2 the stress strain. So it is that area under the curve that we are going to be talking about. As something is loaded, we can calculate based on that what we expect the energy return to be. And think about a rubber band, a spring, a trampoline. So if I jump up and land harder on a trampoline, the trampoline should push me back up higher again. As I hit a spring or a rubber band, the more I stretch the rubber band, the further I expect it to go because there's more stored energy within it. Now, so taking this further, let's talk about how inefficient our system, the human structure, the human body is. And when we look at this graph, before we start talking, all this stored energy does not return, right? Now we know that energy is not created nor destroyed, but it can be transferred, right, to other forms of energy. And the human structure is very inefficient, and this goes mainly a lot with the ability to return the energy that is stored within the system as it's loaded. We will talk about it from a running perspective a little later on in class, but the important part is when the stresses are removed, we don't receive all that stored energy back in the same way that we had it or received it. So what happens to this heat? Well, this energy is, one form is heat. There's a massive amount of heat that we produce in our body from this concept of stored energy loss. But how do we calculate that? And one way we do that is by creating these stress-strain relationships. And if you can see this arrow here, this tells you the direction. So this top line is what happens when we apply the stress, right? So it comes up, and this is where the stressor is removed, and we'll call this point stress removed, right? And what you see now is going back the other way, then this line on the very bottom is the amount of what the relationship looks coming back. And then you have this region down here is that energy that is recovered. Now, if I was to take this original one, this would all be the energy stored, including that white component down there. So how do we identify what was lost? Well, very easily, we're going to take the area under this curve, and we simply do that by calculating the energy stored as 1/2 stress strain minus the energy returned or energy recovered, which is also 1/2 stress strain, and subtract the two, and we have a concept called hysteresis. Hysteresis is the amount of energy that is lost following removal of the applied stressor. So when we do footwear testing, we often do it in this direction. And so a couple components happen, and this is an impact tester by Max Exeter's group, and I've had some fun with this, but essentially what you do is there's a load cell here. Let me change this color so you can see it better. There's a load cell here of a known mass. This will lift up to a known height. So we have mass times gravity times height. We know what a time it hits this shoe, right? So mgh will be the kinetic energy as it's, or potential energy, and then when it hits, we'll have 1/2 mv squared, which is going to be the kinetic energy. And by calculating the deformation of the shoe based on how much it falls, we can calculate how much stored energy. And so what happens is, because of the height and the depth of this, the stress is calculated. And so one shoe may look something like this. Actually, let me change it a little bit. I don't like that one. So one shoe may look something like that. Another shoe may look something like this, right? And then another shoe may look something in between, but really have a small hysteresis. So there's a few things that we would be able to talk about with this, right? And so one of the things we look at when we do this stress strain curve in shoe testing is being able to identify which shoe is more stiff, more compliant, or which one has the greatest energy return, right? And so hopefully from these three and our talk now, you would be able to describe those independently. So the blue shoe is more stiff because it requires a greater stress to produce a certain amount of strain, and you can tell that by the slope of the line. So if let me go ahead and pull yellow. This is the elastic modulus here, right? So we have rise over run versus the elastic modulus of the red, right? So blue slope is greater than the red slope, so therefore the stiffness of the material is greater. One of the other ways you can also see this is simply by the maximum amount of force and the maximum strain that it produced. So shoe blue had a greater stress that was applied to it, but it had a smaller deformation, where red had a reduced stress applied versus blue, but it went through a greater deformation, right? So therefore, blue is said to be a stiffer material than, or shoe, than is red. Now, if we asked the question about which one had the greatest energy return, very easily we could look at this one and say it was green, because this region in the center, which is the hysteresis, is virtually non-existent for this footwear. Where the other ones, it'd be hard to compare blue and red without having it calculated, because they both have a good amount of hysteresis there. So hopefully this helps you out quite a bit. But what I would do is simply go back and try to do this yourself and look, and maybe I'll post a couple more examples of actual footwear testing, because we have quite a bit of see it. And now some materials too will go the opposite way, right? So it'll be like this. But just go ahead and spend some time with stress and strain. I think this is a very important concept that many equipment and strength and conditioning people and physical therapists should be able to identify when it comes to sport movement.